Welcome to the final topic of Module 2, Instrumental Methods. In this lecture, we will discuss the difference between qualitative and quantitative analysis. We will also discuss simple separation techniques that are common in forensic science when examining different samples. We will also discuss various instruments that are used in the forensic science laboratory, chromatography instruments, and also specs. Many microscopic methods of analysis are also combined with instrumental methods that might be used in a forensic laboratory. Appropriate methods to determine the chemical and physical properties of the various samples that they're working with. Several different instruments can be used to gain the necessary information about the samples. Most of the testing is done to either determine the qualitative or the quantitative analysis of the sample itself. If we talk about qualitative analysis, it's actually to identify the sample. So is a certain stain blood, or is that certain stain more of a rust component? If we talk about the quantitative analysis, we're determining the percent of that sample. So if it is a drug sample such as cocaine, how is actually cocaine and how much of it is actually filler material? A wide variety of instruments can be used in the forensic laboratory to determine these properties of the various samples. These can be divided into three main headings: simple separation methods, chromatography methods, and spectroscopy methods. The simple separation methods are necessary to separate a mixture into its components so that each of the components can actually be identified. This can be accomplished through several techniques in the laboratory, either through filtration, distillation, or through extraction processes. A gravity or a vacuum filtration process is used to separate solids from a liquid. A very simple example of this would be when we brew either coffee or tea, where the boiling water is allowed to pass through the solid material. So when we use this in a laboratory setting, that liquid sample is poured into a container that has a filter, which is going to collect the solids and allow any liquids to pass. In some instances, the apparatus may also be hooked up to a vacuum, which can cause the filtration process to occur more quickly. Some samples can also be separated through distillation, and usually this is performed to separate a liquid from a liquid mixture. To do this, the liquid sample is heated, which is going to cause some of the sample components to become vapors, which would pass into a condensing column. The column is cooled so that the vapors entering the column are going to return back to a liquid state, which allows them to be collected and separated from the liquid mixture. In most instances, samples are going to be separated through extractions in a forensic laboratory. This can either be done through a liquid phase extraction or a solid phase extraction. When we talk about extractions, two of the terms that are going to be commonly used are analyte, which means the sample that needs to be separated, or solvent, and this is going to describe the liquid or
the material that's going to dissolve or separate the analyte from that mixture. Solvents can either be water-based or organic-based. In the liquid-liquid process of extraction, this involves the distribution of the compound between two different liquids, one which is usually water and the other which is usually an organic solvent. By taking advantage of the sample's solubility, you can selectively transport that sample from one liquid phase to another. In this extraction process, the aqueous phase, which is usually water, is going to be combined with an organic solvent. Usually the two liquids are then shaken so that the analyte can be distributed between the liquid that it's going to be soluble in. Once the two liquids are allowed to settle, you're going to have two separate layers. The denser layer will always be on the bottom of the container. The analyte will separate into the layer that it is soluble in. And because the two layers are going to be completely separate, then each layer can be removed and then analyzed for the compound itself. In a solid phase extraction process, it takes advantage of the analyte having more attraction to different materials. So you take advantage of the solvent, which is going to be the mobile phase, but then also a stationary phase, which is going to attract that analyte to allow for the separation of the materials. When performing the solid phase extraction, there's a cylinder very similar to the one on the slide that contains that slightly small area of solid material, which is going to attract that analyte and trap it. The column itself needs to be conditioned, so usually there's going to be a series of liquids that are passed through the column to wet the material. Then the sample will be added into that cartridge itself, and depending on the interaction between the analyte and that stationary phase, some of the materials are going to be absorbed into that stationary phase and retained, while other materials will be allowed to pass through the cartridge itself. Once the sample is loaded, usually it's washed a few times with the same material so that all of the impurities will be removed from the cartridge itself before the analyte, which is trapped in that solid material, is going to be washed through. So once some of the impurities have been washed, then a different solvent is going to be added into the column to allow that analyte to be extracted from that solvent, the solid material. Another technique that is commonly used is chromatography. There are several different types of chromatography which we will discuss. All of these rely on the same principle. Chromatography is going to separate materials between the stationary phase, once again, and a mobile phase. The stationary phase is going to, in most instances, be a very finely ground solid material, or in some instances a liquid that's going to be contained in an analytical column. The mobile phase can either be a liquid or a gas under pressure. The mobile phase is going to carry the analyte through the stationary phase. And very simple to our solid phase extraction process, depending on the affinity or the likeness of the analyte to the stationary phase, some components are going to move through that column at different rates. So components that are very different from the column itself are going to move through more quickly than components that are a lot like the column itself. This principle can be applied to the various chromatography methods that are utilized in a laboratory, either thin layer chromatography, gas chromatography, high pressure liquid chromatography, or electrophoresis. With thin layer chromatography, the separation is done through a stationary phase that is a thin layer plate that has been coated with usually a silica type material. The plate itself is then placed into a tank that contains the mobile phase, which is usually a solvent mixture. Through a capillary action, the mobile phase will rise up the plate, separating the different components of the sample. In this separation technique, most of the time there are going to be visualizing samples or sprays that will help visualize the actual samples as they're separated. And you can obtain results very similar to what is shown on this slide. Another chromatography method is gas chromatography. This separates mixtures by injecting a liquid sample onto an analytical column, which is the stationary phase. The separation occurs because of a gas that's going to push the samples through the column itself. So the liquid sample, which contains the analyte, is going to be vaporized at a heated injector. The column is going to be heated to keep that analyte in a vapor phase as it travels through the column and then to the detector. There are usually two common detectors that are used on gas chromatographs, either a flame ionization detector, which relies on carbon-containing compounds exiting the column, which undergo a pyrolysis by a flame, or a thermal conductivity detector, which relies on the thermal conductivity of matter passing around a tungsten filament that has a current applied to it. The data that you obtain from a gas chromatograph looks very similar to that on this slide. There are some gas chromatographs which might be equipped with a pyrolysis unit. This unit allows solid samples to be injected into the gas chromatograph. The samples are placed in the coil filament, which is then placed into a heated component that is on top of the injector port of the gas chromatograph. But this allows solid materials to be vaporized and then to enter that injector to be separated by the column. Some gas chromatographs may also have a special detector attached to them, a mass spectrometer. The mass spectrometer ionizes the chemical compounds as they're separated from the gas chromatograph. They measure the mass to charge ratio of the compounds, which allows for the identification. So with this type of instrument, a gas chromatograph with a mass spectrometer, you get two different forms of data. You get the chromatogram on the left that shows the separation of the materials, but then for each peak on the chromatogram, you can also obtain the mass to charge ionization data, which is shown on the right. There is also a high-performance liquid chromatography instrument, which is commonly referred to as an HPLC, that can also separate materials in a forensic laboratory. This separation occurs where the liquid sample is injected to that analytical column, but then it is pushed through that column by another liquid or mobile phase. The detector that's used on a HPLC is usually an ultraviolet detector. So this detector is going to measure the analyte's response to ultraviolet light, and you obtain data very similar to what is shown on this slide. The final chromatography method is electrophoresis. Electrophoresis separates materials by use of an electric field, and this could be done through two different methods, either by taking advantage of a gel or by taking advantage of a capillary. The gel techniques are very similar to thin layer chromatography. The capillary technique is very similar to HPLC. The data that you obtain for these two techniques is shown on this slide. The data that is on the left-hand side of the slide is what you would receive from gel electrophoresis, and the data on the right-hand side is what you would receive from capillary electrophoresis. Another common instrumental technique that is used in addition to microscopy and the various separation or chromatography techniques is spectroscopy. Spectroscopy is the study of the interaction of matter and radiated energy. The difference in the areas of the electromagnetic spectrum, which is shown in the middle of this slide, is the frequency of the wavelength. As you can see, the radio waves, which are on the very left-hand side of the electromagnetic spectrum, are a lot longer than the wavelengths that are shown on the right-hand side of the electromagnetic spectrum. Wavelength is the distance between corresponding points on two adjacent waves, and frequency is the number of waves that pass a point in a second. All matter consists of atoms. When a sample absorbs energy, those atoms are going to tend to rearrange themselves. So if we think of the atom as being the yellow circle in the example, you can see as the energy is applied to the matter, the energy being the blue line coming in and hitting the matter, it's going to cause the atoms to rearrange themselves. As you can see in the second circle, that yellow circle has moved to a different orbit. Sometimes, depending on the energy that is hitting the matter, it can cause that atom to either just have vibrational movements, or it can cause it to actually move to a separate orbit, like shown in the example. Depending on the sample's atomic structure and the wavelength of radiated energy that is hitting the sample, each sample is going to absorb or react slightly different. So we can think of this as the matter being a set of steps. So as the matter is hit with the radiated energy, those electrons are going to fall down to a different step in that complete staircase. Several instruments in the laboratory are used to take advantage of this interaction of samples with the different types of energy. These are your spectrometers. Spectrometers are going to have 5 basic components to them. They're going to have some source of radiation energy, a way to actually select that wavelength that's going to hit the sample. They're going to have a sample holder and then also a detector to convert that energy so that it can be received by a recorder that's going to provide the results. It's the different types of radiated energy that a sample is going to absorb at particular wavelengths that allows for the various types of characterization that is performed by the different instruments, whether it be an infrared, a Raman, a UV visible, X-ray, atomic absorption, or an ICP spectrometer. The infrared spectrometer uses a source that is a laser that provides mid-IR light radiation. This light is going to hit a sample that is held by one of the methods shown on this slide, either a KBR pellet, a gas cell. Sometimes the sample may be just placed on top of the bench and an ATR is going to be utilized, or in some instances the sample may be put on a salt plate. In all of these instruments, that sample holder is going to send the signal from the light source hitting the sample to an interferometer, which is a series of mirrors that are going to allow different wavelengths to hit that sample at different rates. The detector is then going to convert the absorbed energy into electricity that can be mathematically processed and converted to the data printout that we receive. As you can see by this slide, the lower frequency energy that the source is going to provide in an FTIR is going to cause different types of vibrational movement with the bonds of the molecule itself. Since the IR energy is a lot lower energy, those electrons don't move to a different orbit. They just have different vibrational movements. However, these movements can also be classified and allow us to interpret data and identify different compounds. The vibrational movements are going to be very specific to certain amount of energy that is applied to that sample itself. So, for example, the shape of the absorption band that is around 3000 can be different depending on that chemical component that is actually present. A Raman spectrometer is a complementary technique to infrared spectroscopy. Raman involves light scattering instead of absorptions through the vibrational movements. So the vast majority of scattering is elastic, meaning that the energy of the scattered photon is the same as that of the incident photon. So the scattering also causes a vibration that is going to be very unique to that compound. In a Raman, the laser, which provides UV visible light region is used. There's also a monochromator, which is going to select that wavelength, a sample holder, and a detector that's going to display that chemical shift from the scattering of light at the specific wavelength. The data that we receive is going to be very similar to what's shown on this slide and is going to be displayed for a different region, since it is usually a UV visible source that is used instead of an infrared source. The UV visible spectrometer takes advantage of ultraviolet and visible radiation to obtain information about the UV and the color properties of your solid or liquid samples. A deuterium lamp source is what will provide the energy to the sample. A monochromator is also used to separate the wavelengths. Your sample holders can vary depending on if it's a liquid or a solid sample, but the detector is going to always display the intensity absorbed at each wavelength. So you will get data very similar to what is shown on this slide. In a instrument that liquid samples are analyzed, this is a double beam instrument so that a reference cell and a sample cell are both used. The reference and sample cells look very similar to the quartz cuvette that's shown in the top right-hand corner of this slide. And methyl alcohol is used as a reference to more or less take a background from the instrument itself. If the sample is a solid sample, a single optical path is used, and the samples may either be placed on a salt plate, and then a background is taken and subtracted from the sample itself. An X-ray fluorescence spectrometer takes advantage of X-ray radiation to obtain elemental information about the various samples. So an X-ray tube is what's going to supply the radiation to the sample itself. Depending on the instruments, your sample holders can change slightly, and also depending on the sample, different filters can be used to optimize the energy levels. If you know you're looking for a certain element, the filters can optimize your data results that you obtain. The detectors are going to measure the intensity of the excited photons as they return to the normal state. And then a recorder is going to give you data that is very similar to what is shown on this slide. There is also an X-ray diffraction spectrometer that also uses X-ray radiation and can give you information about the elemental composition of samples. This is a little more specific information. Besides just the elemental composition, it also gives you information on the characteristics of the crystalline properties of that sample itself. But it also uses an X-ray tube to provide the X-ray radiation energy. It has a goniometer and a detector that allows the sample to be measured at different angles. It actually rotates around the sample itself during the analysis process. And then your recorder is going to display information very similar to what is shown on this slide, showing the energy intensities at the various angles that the sample is being hit with that radiation. An atomic absorption spectrometer can also be used to emit specific wavelengths of light to your samples to also determine various elements that may be present. The source is going to be different energy tubes that supply a very specific radiation wavelength. So you choose the tubes according to the elements that you're wanting to actually determine the presence of. The samples are vaporized in a flame furnace, and then there is a detector that measures the intensity of that element for which you are testing. The recorder is going to display the data in a graph, and then you also get a numerical value of the quantity of that element that's present. The final instrument is an inductively coupled plasma emission spectrometer that measures the light energy emitted by the excited atoms. In this instrument, an argon torch or a laser is used to vaporize the sample itself. The detector is going to measure the intensity of the element by characterizing the charged particles that emit light when the interaction between that torch and the sample occurs. And then your data is going to display the quantity of that element present. These are the various techniques that are used in a forensic lab, and this concludes our lectures for Module 2.